we chose a direction to analyze them in. All that was our choice. The loops were kind of our choice. We're limited, but we chose two. So we've guessed at a lot of things, but through those guesses, we've got a series of independent equations that we can then use to solve for some things. What happens if we guessed wrong? I would say we did guess wrong. Anybody see proof positive that we guessed wrong? Look at equation number 3. Does that make any sense? Nah, you can't. These are all positive quantities. You can't add 3 positive quantities and get 0. So we guessed wrong. So what? When you run through this, with numbers of course, right? What you're going to find, probably these two terms, we probably guessed wrong on the direction of the current, right? So you're going to get I2 is equal to, I don't know, negative 5 amps. The negative sign just means that I2 is actually going the other way. Now, do you have to go back and fix it? No. You just have to make a note on your answer. The negative sign means that we guessed wrong on I2, right? That's not a big deal. All you really care about is the number and knowing the direction. So you don't have to go back and rework the whole problem. That's what I say, it comes out in the wash. You are going to guess wrong, and it's totally fine if you do. Just make a note, right? I guessed wrong. Oh well, right? It doesn't matter to me. Now, if you're doing an expert TA homework, you might have to just lose a negative sign somewhere, right? Or put one in if it's asking for a numerical value. But when you're analyzing, you don't have to go back and reanalyze everything. From this point on, it's just algebra. It's just solving the system of equations for whatever unknowns you have. Any questions about these? I'll put up a link to there's some example videos on my playlist. I'll put up the link to this because we don't have time to run over a good example. These are not hard. They can get a little tedious when you have a lot of terms. So here's what to expect. You will absolutely have to finish a couple of these on homework, which is up that way. On an exam, here's what to expect. You don't have time to solve this whole problem algebraically, but you do absolutely have time to write down these 3 equations and then not solve them, right? As long as they're solvable. The physics is done, right? So usually, if I test Kirchhoff's laws, which is not definite, if I test them, it will be a situation where you tell me where your currents are, you tell me where your analysis loops are, and then you write down these equations, but you don't try to solve them. That is doable in the amount of time you'll have. But you should be able to solve these, right? This is just 3 equations for your unknowns. Okay? And how you solve them is up to you. Substitution, matrix, whatever. See linear algebra for details. Questions about this? Kirchhoff's laws work in a lot of different situations, including the one we're about to look at. So, is there any questions about this? Ask them now.
Is it just those 2 laws?
Yep. Now, the first one usually generates several equations. The second one can generate several. It depends on how complex your circuit is, right? But yeah, these are Kirchhoff's laws. Okay. Then let's talk about what happens when you put resistors and capacitors together. And really, there's no way to do it, there's no way to not put them together. Because the wires you use to connect the capacitors to the battery have resistance, right? So really, you will always have that. Now, we don't, your book has uses Kirchhoff's rules to actually derive the equations I'm about to talk about. It takes a little bit of differential equation background. If you have that, it's not bad, it's just a separation of variables. If you don't have that, it's in your future. I would encourage you to look through it. It analyzes it using the rules and then uses that to develop a series or an equation that is solvable. but we're not going to do it. It's a little beyond the scope of this course, and in the interest of time, we're not going to do it. But I am going to give you the equations that will come out of it, the solutions to those differential equations, and we'll talk about. First thing to see is something really interesting happens, which I'm also not going to show you explicitly. If I take the unit of resistance, well, I shouldn't do that, which is an ohm, and I multiply it by the unit of a capacitor, which is a farad. Now, both of these have a lot of stuff wrapped up inside them, right? Anytime a unit is named after somebody, it's because we didn't want to write down the 37 things that go into it. So, again, we're not going to do it. But if you unpack what's inside an ohm and what is inside a farad, and you do the algebraic manipulation of the units, something interesting comes out of this. You get a second. No one saw that coming, right? I certainly didn't. An ohm times a farad gives you a second. And units tell you something about the physics. Turns out, this serves to determine some characteristic time of the circuit. Characteristic of what? Well, we talked about when a capacitor is charging, right? That's a process that looks a little bit like this. You put a charge on basically for free. The first charge comes for free. There's nothing resisting it. But once you have a charge on this plate, then you have to do a little work. It's the same as the potential energy of the charge distribution we looked at, right? You have to work to put the next charge on. And now you have two charges, so you have to work more to put the third charge on. And the more charges you build up on the plates, the more you have to work to put them on. So what we expect is that there to be some sort of time for this capacitor to charge. Some sort of time that we could use to characterize it. It turns out to be given here. The resistance of this circuit times the capacitance is equal to what we usually call tau, the Greek T, right? Which is otherwise called the characteristic time. Now, this is not the time it takes to charge fully. Turns out to be the time it takes to charge to about 63%. It's not an arbitrarily chosen number, but it seems like it is. But it's the characteristic time of the circuit. That's good news, especially for engineers trying to do applications, because if you need a particular time for your circuit to charge, right? If you're building a windshield wiper, you need it to go once every 2 seconds, right? You need to know the characteristic time. You get to choose the resistors and capacitors you put in to make it do that. Right? This is a real simple example that we all see in the timing circuit. They get a lot more sophisticated than that. But we all have seen windshield wipers on intermittent times, right? How do they do it? Well, different resistors and different capacitors. This is the characteristic time. How does that come into it? Well, again, without getting into the differential equations, maybe we can see that if we're charging this capacitor, we expect the current flowing to the capacitor to kind of tail off over time. When I first start charging it, this current going all sorts of ways, because it's easy. There's no charges to resist it on the capacitor yet. So I start off with a pretty large amount of current. But then as I start feeling more resistance to that current, it tailors off, right? Eventually it comes to 0. But mathematically, we're going to represent that like this. Right? A decaying function. We're going to choose to represent it with a decaying exponential. That is the solution that comes out of the Diffie cube. So let me just give you the expression and then we're going to talk about it. For a charging capacitor, we have this. Okay. Of course, you can write this like that. Doesn't matter to me how you write it, as long as you understand that this tau is your characteristic time given by RC. All right. So we have the decaying exponential here. We know it's decaying because the argument of the exponential function is negative, right? If this were not negative, it would be not decaying. I can't think of the word. It would go the other way, right? It would exponentially increase, right? Sorry, I can't think of the actual word. Compound, thank you. I said thank you, nobody said thank you myself, right? It would compound, like compound interest. This is just a compound interest formula with charges instead of principal monies. The decaying exponential given by the negative, this 1 minus is interesting, so we'll talk about what that is. Let's talk about what this looks like though at the limits. We're going to start our stopwatch when we start charging it. So at t is equal to 0, in other words, right when we start charging it. Let's see what we get here. Well, one more thing. The lowercase q is the way your book handles changing quantity. So the charge of the capacitor is changing as a function of time. So instead of uppercase q, they're going to give you a lowercase. Once it's charged, it charges with some uppercase q. We'll see the same thing with current in just a second too. So that's what the lowercase means. Charge is a function of time. It's equal to CE. We'll worry about that in a second. 1 minus e to the minus 0 over tau. Right? At t is equal to 0, this is what I get. Well, 0 over tau is what? 0. Right? So minus 0 is 0. So this boils down to 1 minus e to the 0. What is e to the 0? 1. What's 1 minus 1? 0. What's 0 times anything? 0. So how much charge is on the capacitor at time is equal to 0? None. Isn't that what we said? Like that's when we start charging it. We start our stopwatch when we flip our switch. Alright, so that works. Let's look at it the other side. I'm going to write this. Hopefully we know that that's mathematical gibberish. It doesn't actually mean anything. Because infinity is not a number. Right? It can't be equal to infinity. It's nonsense. What we're saying, t really big. That's what a physicist means when he writes that. T something huge. Right? Okay. What happens there? What is e to the something minus really big?
0.
Practically 0. Right? What is 1 minus 0? 1. And what is 1 times CE? What is CE? Well, definition of capacitance. Right? V is being played by script E. Remember, EMF is just voltage. So this just tells us things we already knew. At the beginning, before I start charging it, it's not charged. Yay. After I charge it, it's charged. That's all this says. So, useful for the times in between. Not really at the extremities. But it's a nice way to check ourselves. So this is the charge that appears on a capacitor as you're charging it. Now, there is a different equation, similar, for a discharging capacitor. Things work a little differently there. We'll get to that later. Any questions about this? I will say, normally, the easiest way to handle these is by, so you might see something where it says, what's the charge on this capacitor after 6 microseconds? Well, the right way to handle that is to express your time in terms of your characteristic time. So, like this. Let's say that you run the calculations, you do RC, and you come up with that tau, and I'm just picking these numbers at random. Let's say that tau is 2 seconds, right? And then you're asked to find Q at 6 seconds, right? The easiest way to handle that is to recognize that T here equals 6 seconds, but that equals 3 tau, right? It's easiest to express your time, and this isn't physics, this is just practical advice. Express your times in terms of your characteristic time. Because then when you go to plug that in, right, you do it here. Minus 6 tau. I just got to put right minus 6. It's an easy way to handle it. You are welcome to not do it that way, but that's a lot of punching into a calculator. I would do it this way. Just me. Okay? Questions about these? Again, the derivation of those equations is what's hard. Using them is not. That's the charging capacitor. You can also find equations for, and we will, for the current that is flowing through the resistor as a function of time, right? So if you're charging a capacitor and the flow of charge is changing because the capacitor is resisting it, then certainly the current that's flowing through that resistor is also changing as a function of time. Also given as so obviously if these two expressions are equal, E over R is equal to I naught. Where does that come from? Where again V is being played by square T. Right? So this just boils down to Ohm's law, but we're letting the current taper off because we have an increasing amount of back voltage, if you want to think of it like that. We have a voltage degree across the capacitor that's opposing the flow of charge. These two equations are valid for charging capacitors. Right? Your book is also going to give you one for voltage appearing across the terminals. All these work the exact same way. They're all exponential functions. Now, let's talk about the discharging formulas. Again, I'm just going to give them to you and then we'll talk about it. I'll leave this one. Now, when you're discharging a capacitor, in other words, you close the switch and charge starts flowing. Something similar is going to happen, right? Initially, the charge goes pretty quickly because all these charges that are built up on the capacitor don't like each other and start jumping ship. But as there are fewer of them on the capacitor, there's less and less impetus for the ones remaining to get off. And so you again see this thing that goes down exponentially. So we'd expect the charge on the capacitor to start off at a full value and end at nothing. We'd expect the current to start off robust and end at nothing, right? So actually somewhat similar, the current acts just like it did for the charging capacitor. All right, so for discharging capacitor, charge is a function of time. Right. Where this Q is just the C. Right, that's the same value. I'm just giving it to you slightly different form. You still have the characteristic time. You just don't have the 1 minus. That mathematically serves to tell you that at the beginning, it's not 0, it's the full value Q. As T gets bigger and bigger and bigger and bigger, then you have e to the negative, something really large, goes asymptotically to 0. Okay. All right, and the current will work the same way. It's actually the same formula. Questions about any of those? One more thing to talk about before we get out of here. No, we actually don't have time. Okay, we'll finish that next time. You do have 30 seconds if you have questions about this stuff. All right, there's one workup over all of this stuff. How to get started on it, and this will be the material and the capacitors that'll be on your exam on Friday, and what we finish up here on Wednesday.